So, spectroscopy. You've had some doses of it, but there is a lot more to talk about. All spectroscopy is the study of how matter and electromagnetic radiation interact. The way that we're using it is to determine structural information about molecules that we make, say, in lab. All right? So last semester, if you were with me in class, you might remember IR, and you might remember how much you loved it. You also had a little bit of a dose of it in lab. But we have two other spectroscopy techniques that are going to be really useful because IR only gives us a little bit of information. So typically when we're talking about the three important spectroscopic methods in organic chemistry, we start out a lot of times with mass spec, right? So mass spectrometry, the idea is that we get a mass of a molecule, and from that mass, we can actually determine molecular formula. And that's the main thing that it's used for. It just tells us whatever that molecular formula is. Now, there are ways that you can utilize mass spec with things like fragmentation, which we will talk a little bit about, in order to get a small amount of structural information. However, that is not realistically what we want you to get out of this class. Being able to do a little bit of fragmentation, great. That means you're in a good position. But just getting the molecular formula is the primary way we're using mass spec. And so the next two lectures are going to be devoted to how can we read mass specs in order to get molecular formulas. IR, if you remember from last semester, all it tells us is what functional groups are present in the molecule. Right, because whenever we looked at those IR stretches, we were looking at things like, oh, we have an OH stretch. That can be an alcohol. It can be a carboxylic acid, et cetera, et cetera. But it never truly gave us super strong information on what the full structure was. That's why previously in organic, what I was doing with the class was I was saying, you can just propose a structure, and as long as it follows the appropriate functional groups, that's a reasonable one for the IR. Where we really get into the weeds of things is with nuclear magnetic resonance spectroscopy, right? NMR is super important because NMR gives us the most information out of any of these. It tells us how atoms are connected in a structure. So realistically, using NMR is going to be very nice for being able to determine what the structure looks like without having to second guess anything. There's not multiple possibilities there. But the thing is, about each of these, they provide some sort of information that you can use to build a better idea of what that final molecule is. So using them all together is a good thing, right? When we actually take IR, mass spec, and NMR, we put them all together. Hopefully you'll become Avatar the Last Spectra Bender and you'll be able to use all three of them to their max capacity. If you master each one of them, exam 1 is actually going to be pretty simple. All right? But that's if you master. I can say that about any exam, right? But the good news is, the way that I've changed up the lab course here for OChem2 is that we are utilizing these starting labs to support the information that we see in these lectures. All right, so we're going to have an unknowns lab that's essentially a pre-exam 1, pretty much practice exam, where you're working hand in hand with the spectroscopy. All right, but to get there, we have to understand what each of these do. So mass spec is where we're starting. Mass spec, the whole thing it does, it measures the mass of a molecule by exploiting two physical properties. The first one is the most important one, that is charge, right? Charged things are what we're actually measuring in the mass spec. And then the other one is angular momentum. If you wanted to become a physicist and learn all about mass spec, you can have fun. We're not going to go that deep into it. But the idea is that things with more mass get deflected at different speeds. And that's how we're actually determining the mass. But the big thing is that idea of charge. So how does a molecule become charged in a mass spec? Well, here we have a diagram of what a mass spectrometer actually is doing. And there's really 3 stages to this instrument. And again, as I had said back in OChem 1, but you're going to hear it again in OChem 2, you do not need to be super familiar with exactly the inner workings of all of these instrumentation pieces. All right, I'm showing this to you to give you an idea of what it looks like and what's happening, but I'm not going to quiz you over everything that we see right here. So In a mass spec, the first thing we do is what's called ionization. We make the molecule charged. We then shoot it down a really fun little tube that has electromagnets on either side of it, and that's going to deflect that molecule some angle. That's where we get that angular momentum coming in. And then the detection is when that molecule comes down and hits the detector, we see it, and that tells us what the mass of the molecule actually is. All right, so that's all the mass spec is doing. Charging it, launching it, and then seeing what the mass ends up being. The big thing that we actually care about for organic is what's happening during that first stage, ionization. Because ionization is where we actually get charges on the molecule, and it helps us determine what the mass is later on. So the idea of ionization in most mass spectrometers is they're all measuring positive charges. The way they actually make something a positive charge is they just shoot a beam of electrons directly at a molecule until they knock one of the electrons out of it, right? So, for example, this down here, we see this carbon-carbon single bond. We have electrons being launched at it, and one electron is going to get ejected from that bond. What this ends up doing is a practical representation would be we start out with C2H6, and we throw an electron at it. After it knocks an electron out of the molecule, we end up with C2H6, but now it is a radical. A radical is an unpaired electron. If we're getting one electron out of this thing, we're going to have an unpaired electron. The other thing is we have lost an electron from the neutral molecule. So anytime we're losing electrons, keep in mind, we're going to end up with a charge. It's going to be a positive charge. So what we've generated in this case is called a radical cation, right? And so radical cations are really weird because they don't really exist outside of mass spec, right? The other thing that you can keep in mind that we've ejected here is we do get that other electron. So we now have a pair of electrons that goes off into the ether and they get dealt with later on. But radical cations, in and of themselves, they're super unstable because you're pairing a radical, which is already super unstable, with a cation that is also super unstable. Both these things together make a very uncomfortable species that doesn't really want to exist. But it can exist for long enough that we're able to actually see it on the mass spec. Okay, so is everyone cool with how a mass spec do its job? Okay, so let's look at how we actually work with these things, right? The radical cation then goes down the chute, it hits the detector, great. What we should see is a mass. That mass is going to be from the atoms that are present in that given molecule. And so when we're looking at these masses, I want to remind you that you can look at the periodic table to get the mass of literally any atom. But these ones right here, carbon, nitrogen, oxygen, hydrogen, they're the ones that we typically see in organic. We're going to talk about some other ones as we go, but this is where we're going to start. So as a reminder, if you look at the periodic table, you'd find that hydrogen has an atomic mass of 1, approximately, carbon, 12, nitrogen, 14, and oxygen, 16. So whenever one of these molecules hits the detector, we can determine what atoms are present just by adding these masses up. So let's take, for example, the one that we just launched at it from that previous example, ethane, C2H6. What will the mass be that pops up on the mass spec? Well, all we have to do is we have to add up the masses of the carbons and hydrogens. This is stuff that you did back in Gen Chem to find molecular weights, right? We would say that in this molecule, there are 2 carbons, right? If you multiply that by the mass of the carbons, which is 12, you end up with 24 AMU, right, atomic mass units worth of carbon in your sample. Hydrogens is the same idea, but we have 6 of them in this case. It's only 1 AMU apiece. You end up with 6 atomic mass units. Add those up, what do we get? Well, we get the total in this case is 30 atomic mass units. So when we launch this thing through the mass spec, what we would expect to see is something pop up that says we have 30 atomic mass units worth of a molecule in there. And this is the same for every molecule that we can shoot through mass spec. It's just a difference of what atoms are present within that mass. All right, so this is how we're actually going to be calculating things when we're talking about mass spec. Is everyone cool with that? Okay. The thing is, this is what we actually see. Because spectroscopy can never be as easy as a single number, right? This is the output of the mass spec for ethane. All right, so the same molecule we were just talking about. And you'll notice that throughout this entire spectrum, there are little red lines that jump off of the base x-axis. Those are the peaks in the mass spectrum. And you'll notice they show up at multiple different locations. The thing is, when we're looking at each of these mass specs, we're essentially looking at things in terms of the intensity of what hits the detector. So notice on our x-axis, we have something that's labeled M to Z, or M over Z. This is what's called the mass to charge ratio. Here for organic, we are not going to go super deep into mass to charges that are not just a charge of 1. We're assuming every molecule we play with has a +1 charge. So M to Z, that is just mass for us. Okay? When you start to get into biochem and proteins, that definition changes a little bit, all right? Because it is normalizing the mass based on the charge. Again, it's just mass for us here. And then that intensity tells us how many times that thing has been detected in the mass spec. And you'll notice that we do have what we expected showing on this mass spec. There we go, right at 30. Great. This is what we expected. However, we also have all this stuff that we may not have expected. Because everything that falls below all of these peaks and all this other stuff down here, this is called fragmentation. And so fragmentation is realistically what we're talking about next lecture. So the first thing you might ask yourself is, all right, if I get one of these, what am I thinking about? Because what are you paying attention to, right? First thing you want to find, you want to look for what is called the molecular ion peak, which we label as that M in brackets with a plus beside it. The molecular ion peak is the thing that gives us the most information from the mass spec. From there, we can look at the base peak. We'll talk about what it means, but it can be the same or it can be different from that molecular ion peak. It's another indicator that tells us a little bit about structure. And then the last thing we're looking at is other key fragments in the mass spec. All right, but again, that's going to be for next lecture. So let's talk about that molecular ion peak. The molecular ion peak is the peak that tells us the actual mass of the molecule itself, right? That's why it's called the molecular ion, because it's the entire thing just with a positive charge. And so usually when we're looking for molecular ion peaks, it is the furthest right-hand peak within your mass spectrum. All right? And if we look back at that one for ethane, you can see that this does line up because the same peak that we had labeled above, notice there's nothing else to the right of it. That is the molecular ion peak. And so this one will always tell you what the weight is of that given sample. And so when we were talking about that calculation above, we said that C2H6 radical cation should have been 30 AMU, and that means that the M plus peak for the spectrum also should have been 30 AMU. Now bear in mind, we're looking at this spectrum with the idea that we know what's already there. But what I'm going to be asking you to do on quizzes and exams, and we're going to do some practice with it, is looking at a spectrum and finding that molecular ion peak and then telling me what the mass is. Not the other way around like this, okay? So that's why it's very important to see this. One of the things that you'll notice, though, is sometimes it is not the furthest right-hand peak because we have things that are called the M plus 1 and M plus 2 peaks. Because molecular ions are fantastic, but we also have isotopes that can change that mass. So for example, carbon, it has two isotopes. Carbon-12, which is the one that is most commonly occurring in nature, it makes up 98.9% of all of the carbon in the world. We also have carbon-13. So remember, an isotope is just a difference of neutrons, right? No difference in reactivity, it's just one extra neutron added there. And so this one has one additional mass unit compared to carbon-12, and this one shows up as the other 1.1% of the time. And whenever we look at these two compared to one another, this set of percentages actually tells us a little bit of information. It says that 1 out of every 100 carbons will be carbon-13. And so what that means is that if you have all of these molecular ions and you're launching them at the detector, 1 out of every 100 of the carbons that is there is going to be 1 unit higher. And since we have something that's 1 unit higher, we end up seeing the M+1 peak. Take, for example, that same idea of ethane as we saw before. Right? The original thing that we actually calculated was the C2H6, where both carbons that were present were C12s. Right? Since these were all C12s, we ended up with that mass of 30 AMU. And that was our molecular ion peak. But there is that 1% of the time that one of those will be swapped out. And so instead of both being carbon-12, we'll have one carbon-12, one carbon-13. The hydrogens are always going to be the same. In this situation, with one C13, we end up seeing this would be 31 AMU. So that's the idea of our M+1 peak. Now remember that since this is a difference in terms of the percentages that these show up, the M+1 peak is not going to be like absolutely massive because it's 1% of the time. But what you would see is if you were to really zoom in on that ethane mass spectrum, I mean, my art is absolutely beautiful, you end up with what you see here. You have that peak at 30, and then you have this really mini peak at 31. And so that's our M+1. But since there's so much less carbon-13 present, that peak is very small. It is also a probabilistic thing, so the more carbons you have in a structure, the bigger this peak will be because you're raising the probability that one of those hits is carbon-13. Okay? But keep in mind that this will always be the case where your molecular ion peak will be bigger than your M+1 peak. All right? So M+ will always be taller than your M+1. Is everyone comfortable with that? At least a little bit. Okay. Then let's do an example of it. I'll try not to scroll down all the way there. I'll zoom out a little bit for those still writing. We have another mass spectrum down here. Let's say that we were to try and determine what the molecular ion peak is. First thing I always say to do, look on the far right of that mass spectrum. And then pay attention and say, okay, which peak is it going to be? Well, we have multiple peaks over here that are all clustered around the same area. But notice that this guy right here, he's pretty short. Right? The one directly to the left of it, that's only 1 unit different, is much, much taller. And so when we look at this, this is an indication that small peak is not our molecular ion peak. It must be our M+1. Right? The one that we have highlighted in red, that would be our molecular ion peak. This would be our M+1. So in reality, whenever we're looking at this molecule here, we would say that our molecular ion, the actual mass of this molecule, must be 92. Because the M+1, we realistically don't care about at this point. Right? We've just eliminated it as the possibility for the molecular ion peak itself. Make sense? Fantastic. Well, this is also a spectrum that we don't know the formula of yet. Right? Because I haven't given it to you. You don't know what the molecule is. So, how can we determine the formula? That's what the rest of these mass spec lectures are meant to do. It's how can we determine what atoms are within a molecule given the formula that we have. Because again, that is the most important thing that we're getting out of this. So with that in mind, our M plus of 92 AMU, let's talk about how we find formulas. What I have written here is technically a step-by-step on how to do it, but there's kind of an implied step that comes before this that we're going to see in the next lecture, which is if you know the identity of some atoms that are already present, you can actually subtract those out before doing some of these steps, which I will show you how to do. But for right now, we're just going to say, all right, let's assume that there's just carbons and hydrogens here, and let's figure out what the formula is of this structure. The first thing you're going to do is you want to determine an estimated number of carbons that are present within that structure. To do so, we can follow something called the rule of 13. The way this works is if you divide the mass of the molecular ion peak by 13, and then you round down, you have an estimate of how many carbons are there. This works because when we think about our molecular ion and the mass of carbon is actually 12. But by dividing by 13, we're actually accounting for a couple of hydrogens to make sure we have some wiggle room. Since it's an estimate, it's not always going to be perfect, but it'll be pretty dang close most of the time. So let's take this with the 92 that we just had up there and see what we get. 92, if you divide it by 13, what you're going to end up seeing is that you come out to 7.07 number. We don't care about anything past that. Because again, we're going to round it down. Right? So rather than being 7 point something, if we go ahead and do some rounding of this, we would say that in this structure, there are 7 carbons. Right? That's our estimated carbon count. So we're going to utilize that as our basis behind our molecular formula. And again, we can change this later, since it's just an estimate. So keep in mind that you do not need to stick with the exact number of carbons that you have originally. Most of the time it'll be pretty good though. Okay, second thing you do, now that you have an estimated mass of carbons, take them and you want to determine the mass of those carbons. All right, so we're just using the same things that we did beforehand to say, all right, if we have 7 carbons, and they're all 12 AMU, you multiply those together, what do you get? You get 84. What this is telling us is that from our formula, 84 of the mass units are accounted for from carbons. All right? This also gives us a lean-in on what happens next. We can determine the number of hydrogens using the leftover mass. All right, what I mean by that is our starting mass was 92 AMU. And we used 84 of those for our carbons. All right, so there's our starting and our carbon mass. And so if we just subtract those, we end up seeing that we have 8 mass units left over. Those 8 mass units are the mass of our hydrogens in this spectrum. And the good news about hydrogen is it makes our life really easy. They're all 1 apiece, so you don't even really have to do the math. This 8 mass units is the same thing as having 8 hydrogens. So, from that given mass, we have now estimated an appropriate number of carbons and an appropriate number of hydrogens, right? So that gives us an approximate estimated molecular formula. So our molecular formula estimate is we had 7 carbons that we said we would account for, and we had 8 hydrogens. C7H8. Right? That's what we're going to roll with. So, from here, what we need to do is the last step, which is always make sure that you are double checking that your formula is even possible. Some formulas, you can't do them. Others you can. And so the way that you can really check your work is by comparing things to the DOU within a molecule. So flashbacks to CHEM211. DOU is degrees of unsaturation. As a reminder, these are telling you if there are rings or double bonds in your molecule. And so whenever you're looking at a DOU, you take into account a lot of different atoms. That being, we have carbons. So you do 2 times the number of carbons plus 2, plus the number of nitrogens. So we account for nitrogen. We also have minus our hydrogens and minus halogens. All right, so keep in mind, we can have bromine, chlorine, etc. that are adjusted for there. And all this is doing is it's making sure that we have a DOU that actually exists. The only rules about DOU that are really important in this case are you cannot have a DOU that is negative or a fraction. If you have that, you did something wrong or your estimation needs to change. Okay? So let's do it with the formula that we actually just came up with. Right? Our example was C7H8. If we plug that into the DOU formula, our DOU in this case, it's 2 times the number of carbons, so 2 times 7, plus 2, minus, we have no nitrogens, we have no halogens, it's just hydrogens, so minus that 8 divided by 2. You get 14, 16, minus 8 divided by 2 is 4. All right? So the DOU for this example is 4. That is a valid DOU. Another thing to keep in mind is does anyone remember from last semester what a DOU of 4 typically represents? Aromatic rings. Yes. So typically whenever you see 4 or more, you can think to yourself, this is not only a valid DOU, but it's likely an aromatic ring. Very nice. Now, an example of an impossible formula. Because again, you can get some things a little bit messed up. Let's say that you did your math for something else and you came up with C3H10. If you were to do a DOU calculation on this, you would say, all right, 2 times 3 plus 2 minus 10 for the hydrogens divided by 2. You end up with -1. So this would be an example of an invalid DOU. That means that you can't have something with that formula. So if you were to come up with that and see that number for your DOU, you should immediately say to yourself, that is not possible, and so I'm not going to actually use this as my formula. You can go back and adjust your estimations then. Sound good? Dang, I'm a little fast, because that was everything in this one. But don't you worry. I know. Hey, this just means we have more practice time tomorrow, all right? Sorry, Friday. I got biochem on my mind, because they meet on Thursdays as well. We're starting it. Oh, okay. I'll give you a second to write stuff down. Yeah, I'm trying to make sure that we have more time for practice on Fridays, so I was making my lectures a little shorter, and I guess we're a little short at the moment. Oh, okay. Well, don't worry. We have so much more to talk about. All right. We're going to continue through this one at least a little bit. I know we won't get all the way through this. So what we were just doing with that set of formulas was we were calculating under the assumption that only carbon and hydrogen existed. That is almost never the case, right? So we need rules to help us determine when other atoms are present in these formulas. And we actually have quite a few. So how do we tell if other atoms are present that aren't carbon or hydrogen? The first and easiest one to tell is actually going to be nitrogen. Because nitrogen has a really interesting property to it, where odd masses for your mass spec immediately indicate that a nitrogen is present. All right? So any molecular weight, if it's odd, it has to contain an odd amount of nitrogens. That means 1, 3, 5, 7, whatever it may be. I probably won't go up to 7, but you get the point. It has to have nitrogen. And also the molecule doesn't need to be neutral in that case. Having charges changes things up. I'm not going to give you charged molecules on things like exams. Although I should have done that for your practice worksheet. I might go back and update that. It's good practice. It's good practice. All right, but to give you an example of how this occurs, we can look at the difference between something like ethanol and ethanamine. In these cases, if you take ethanol and you add up the masses of all the atoms that are present, we have 2 carbons, 12 apiece gives us 24, right? We have 6 hydrogens, so that's going to give us an additional 6 to make 30. And then we have the oxygen for 16. 30 and 16 makes 46. So it is useful also to have these molecular formulas written down whenever you're doing calculations, because then you can just add up all those masses. But yeah, like I said, this is 46 AMU. But if we take a look at ethanamine, what we see is that it's a super similar formula, but now it's C2H7N. So even though nitrogen itself has an even mass, it has a valency to where, since it can form 3 bonds, we always end up with that odd hydrogen. And so because of that, our actual calculation for the AMU comes out to be 1 less than what we see for oxygen, just due to the weight difference, but it's also odd. And so anytime you're looking at a molecular ion peak and you see that mass is odd, you can immediately look at it and say, there must be a nitrogen here, because this is always true, that odd equals nitrogen. Okay? So next week, if you're on your quiz and you're looking at it and you see an odd mass and you don't say that there's a nitrogen there, I'm going to be severely disappointed. All right? Because your monkey brain it. You see odd, you go, ooh, nitrogen. All right. That's one of the easy ones. Let's talk about something that is a little bit more difficult, but it still has a very obvious tell. That is halogens. So remember that just a little bit ago I was talking about how we have these isotopic peaks where we have those M+1s. Halogens introduce us to M+2 peaks because halogen isotopes differ by 2 atomic mass units as compared to carbon's 1. Okay? So anytime we see a mass peak and an M+2 peak, we know there's going to be a halogen present. But the thing that actually changes which halogen it is based on the distribution of the 2 peaks. So just like we saw with carbon isotopes, chlorine and bromine isotopes also have percentage distributions. For chlorine, it ends up being that 75.5% of all chlorine atoms are chlorine 35. On the other hand, the remaining 24.5% are chlorine 37. And so from this distribution, we can say for every 1 chlorine 37, there are 3 chlorine 35s. Right? Because it's like a 3-to-1 ratio. Divide 75 by 25 and you end up with about 3. And that's how we're going to essentially use this ratio throughout the class. We're going to treat it like it's an exact 75-25. Because that tells us that anytime we're looking at a mass spectrum, our ratio of the chlorine 35 to chlorine 37 is going to be 3-to-1. And this ratio transfers over to how the peaks actually look in the spectrum. All right? It's the same way with bromine. Bromine isotopes are even easier because bromine 79 accounts for about 50.7% of bromines, and bromine 81 accounts for the other 49.3%. It's practically negligible for us what the difference between those two are. It's a 1-to-1, right? So it's an equal distribution. So our ratio of bromine 79 to bromine 81, we're calling it an exact 1-to-1 for the sake of this course. All right? How we can actually utilize this when we're looking at a mass spectrum is, take for example, chlorobenzene. When we look at chlorobenzene, right, we're looking for that molecular ion peak, but we see that there are 2 peaks down here. One of them is this one right here. The other one is this one right here. And notice the height of those two peaks in comparison to one another. The first tell that we see is they're 2 mass units off of one another. The second thing that we see is this one sits at about 100% intensity, and this one sits right around 33% intensity. That's exactly that 3-to-1 ratio that we were just talking about for chlorine. And this arises simply because when we're looking at that chlorine atom itself, this could be chlorine 35 or chlorine 37. And so depending on which one it is, that gives us that difference in our molecular ion peaks. So the one that's sitting up there at 100%, this is in fact our molecular ion peak due to chlorine 35 being the present isotope in that molecule. But then we also have down here that 33%. This would be our M+2 peak due to chlorine 37. And so you're looking for those tells in the spectrum. You're saying, do we have peaks that are 2 mass units apart? And do they match the appropriate ratio of our chlorine or bromine? Does that make sense? Okay. So yeah, make sure you pay attention to the size of peaks whenever you're looking for halogens, because they will always give us that 3-to-1 ratio. Oh, I have blue and red written down in the notes. I'm sorry. It's red and green now. Given Christmas. So yeah, in this case, since red is 3 times the height of green, that indicates chlorine. Are there any questions about the idea of these M+2s? Because we're going to do one for bromine as well. Okay. Let's look at bromine. The exact same type of molecule, bromobenzene. In this case, we have the bromine, that it's the same idea as chlorine. This could be bromine 79 or bromine 81. Right? So still a difference of 2 mass units. But with bromine, the peaks should be pretty much the exact same height, because remember, it's a 1-to-1 ratio approximately, so they may not be perfect. And you can see on this spectrum, we have this peak right here that's 2 mass units off of this peak right here. And they're about the exact same height. So once again, we can say that this would be our molecular ion peak due to bromine 79 being present. And this would be our M+2 due to bromine 81. And again, the idea of this ratio of them also matters. Since they are equal height, approximately, that indicates that bromine is present. Sound good? Okay. Some of you may be thinking, off the rip, man, oh yeah, what's up, Kaylin? You're right. There was one with really... We'll talk about how that works in a little bit. Okay. Another way to know, though, Caitlin, that's a great segue, is that you also have one other indicator of halogens that can be really useful. It is the halogen mass difference. So whenever you look at a mass spectrum, you have all the peaks there, right? What you can do is, if you suspect a halogen is present, you can subtract the mass of the halogen from your molecular ion peak and see if there's a peak that lines up right where that's supposed to be. Because almost every time you have a halogen present, it will do this in the fragments of your mass spec. Again, we'll be talking about fragmentation a little later. So, looking at something like that chlorobenzene to help justify that it is a chlorine, we already talked about the difference in the peak sizes. We already identified that this right here is our molecular ion peak. Well, this molecular ion peak it's showing up right at 112 AMU. So that's great. We suspect there's a chlorine. So if we subtract the mass of chlorine from that, we should have a peak that lines up with it. And keep in mind that whenever you're subtracting from the molecular ion peak, you want to choose the smaller isotope, not the bigger one, because that is the isotope that's supposed to be present in your molecular ion peak. All right, so we would subtract out, in this case, 35 AMU due to us suspecting chlorine 35 is there. And that should give us a location of about 77 AMU for an additional peak. If we look at that spectrum, and what we see is that there's a nice peak. It's like one of the only other ones over here. And wouldn't you know it, that's right at 77 AMU. So we can actually use this to say, that's pretty dang good evidence that there's a chlorine there. We have the proper ratio. We have the M+2 peak. And we're matching up the idea that our chlorine is gone. Right, so this matches the loss of chlorine 35. So every time you're suspecting there's a halogen, I highly recommend doing this, because you can do the same thing with the bromines up above. This one, you see the peak that lies like right here? Whoops, I'm really bad at drawing it. It's close enough. That is also the bromine mass difference in this case. And you'll notice that almost every single time, it's one of the biggest peaks down in the bottom of the spectrum. So that's another way that you can tell, Caitlin. Because in ethane, the other thing is it couldn't contain a halogen because there's not enough mass there to begin with. Right? Are there any questions about halogens and determining their molecular ion peaks? Cool. All right, there's only one other annoying atom that we have to worry about. How do we tell if oxygen exists in our molecule? Well, oxygen kind of sucks because there is nothing within the mass spectrum that'll tell you that oxygen is present in your molecular formula. Absolutely nothing. So you can look at a mass spec and you can assume that there's only carbons and hydrogens, but it could also have an oxygen in there. But this is why mass spec is great for a lot of things, but starting to pair it with other spectroscopy ends up being very beneficial. Take, for example, pair it with IR. If you have an IR of your molecule, which is the next lectures after these, you can immediately tell if there's an oxygen there, right? It's very obvious every time you have an IR because you have carbon-oxygen double bonds that show up right around 1700. You have your OH bonds that show up further down the line. So that's a great way to figure it out. If you're looking at a mass spectrum and you determine that it just has carbons and hydrogens, double check the IR. We're going to be doing that a lot next Monday. And then the other way that you can tell is what's called high resolution mass spectroscopy. Because whenever we're doing all the calculations that we have been doing, it's been based on just specific isotopes and just saying we're not adding decimals, we're just cutting it off to the singles place. But in reality, every atom that we have talked about has what's called an exact mass. The exact mass actually takes into account every proton and every neutron out to 4 decimal places. And you'll notice that whenever we start getting out to these 4 decimal places, that the numbers actually change. Hydrogen is not just 1, it's 1.0078 units. Carbon actually is exactly 12, so it's kind of nice. But then we have things like oxygen, 15.9949. And so we can start to determine differences between these structures because the atoms aren't necessarily just rounded to that singles digit. All right? To give an idea of this, if we had something like propane and acetaldehyde, right? These two molecules, they're pretty small, somewhat similar. If we ran a low resolution mass spec of this, we just added up all of those isotopes, what we would see is the M to Z that shows up on the mass spec for propane would be 44. The M to Z that shows up on the mass spec for acetaldehyde is also exactly 44. So there'd be no indication that oxygen even existed in either molecule. However, that high resolution mass spec, we'd actually be able to see the difference. One thing that you'll also see, and this is especially true for when we're talking about Dr. Yang's notes, because he does have practice problems that he's going to be sending your way, this is also called monoisotopic mass. Okay, you can call it exact mass, monoisotopic, it's entirely up to you. I call it exact mass, he's more of a monoisotopic guy. All right, so both things mean the same thing. It is how different are those things based on those 4 decimal points. So let's do it. Let's look at the way that propane and acetaldehyde differ. Propane, C3H8. What we would be doing is we'd be saying, okay, well now we're still doing those same mass calculations where we're taking our 3 carbons, but now we're multiplying it by the exact mass, which for carbon is easy. It's 12.0000. And that still comes out to be 36.0000. And so this is still good because we've still done, like we've seen before, our number of carbons times our exact mass of carbons to get our exact mass of carbons within our molecule. We can do the same thing with hydrogens. This is where we start to see that little bit of difference. Because we have 8 hydrogens in propane, and like we saw in that table above, that's 1.0078, right? It is not exactly 1. And so because of that, we end up with a slightly different number than just 8. It's 8.0624 units. If we add those up, we get the exact mass of our molecule, which happens to be 44.0624. Right, so we have a little bit more information. We have those extra decimal points. So how does that compare to something like acetaldehyde? Well, acetaldehyde, we have 2 carbons. Multiply that by our 12.0000. We get, of course, 24 with a bunch of zeros afterwards. We have 4 hydrogens. Multiply those by 1.0078. And you end up with 4.0312. And then we also have that oxygen, which is 15.9949. You add all this up, and what you end up seeing is that this is 44.0261. So these masses are different, right? In a high resolution mass spec, we can tell the difference between these 2 molecules. All right, and since we can tell the difference between these 2, we actually know that oxygen exists in one of the molecules because that mass is slightly different. All right, we can see the difference. Here's the thing. While this methodology is super useful in the research lab, I'm not going to waste your time doing calculations on exact masses for your exams. Because this process takes a while. You got to look up the exact mass, you got to write down a bunch of decimal points, yada, yada, yada. It's not worth your time. So, and the other thing is it's still hard to figure out what elements are actually present in there. So exact mass, if you ever do research in something like organic chemistry or analytical, this will come in super handy. But for us in this course specifically, for identifying if an oxygen is present within a molecule, we're going to be heavily relying on IR. That is going to be our key tell whether or not an oxygen is present. All right, so just to remind you of everything, odd masses are nitrogen. Looking for halogens are that M+2 with those different ratios. Carbon and hydrogen are going to be present in everything, and then oxygen we use IR. So on Friday, we'll continue down this little rabbit hole, talking about a little bit of additional stuff with fragmentation, and we'll be doing practice problems. So come with a pencil. I'll see you then.